Hi there, in this video we're going to look at the trig identity sin x upon x, and we're going to take the limit as x tends to 0, and we're going to show that that limit is equal to 1. Now the reason for doing this is that it cropped up in the signal processing videos, so it's a nice thing to see where it comes from, and you'll see it cropping up now and again. So let's imagine that we had a part of a circle, so let's say there's part of a circle, and let's say the circle has radius 1. So if that circle's radius 1, then we can say that the area is pi r squared. Now r is 1, so you can say the area is pi, so the area is 3.14. okay, now the circumference of that circle is going to be 2 pi r. Now if r again is equal to 1, the circumference is 2 pi, which equals 6.28. okay, so the circumference is twice the area. Okay, now if I was to look at just half of the circumference of a circle, okay, then again the circumference of that half a circle would be twice the area of that half circle as well. Okay, so there's a direct relationship between the circumference of the circle and the area of the circle, and the constant proportionality is 2. okay, now if I was to drop the perpendicular from here to here, right, and we'll call this arc here, we'll call it x. Okay, so that means that that little angle there is x, because it's x is that angle in radians. Okay, then we can see that geometrically this sin x upon x, well, this height here is the sine of that angle, so that there is sin x, and this length here is x. Okay, so we can see that sin x is, well, I'll just write down that there. Okay, that's that length sin x. Okay, and it's the length of the arc x. Okay, now rather than looking at it in terms of these lengths, what we can do is we can look at it in terms of areas, because we know that the length 6.28, the length of the circumference, is directly proportional to the area. So this length is directly proportional to the area, and this length here, so the length of the arc here is directly proportional to the area of this little arc. So what we could do is we could redraw that. Now I'll draw it out again. Okay, well, meant to be a circle. Okay, and we'll take that length there again. That length is 1, and we'll give them some names. We'll say O for the origin. We'll drop the perpendicular here, and we'll call that C. We'll call that A. We'll call that point B, and also if we were to continue up this line here, we could call that D. Now we know that the area of this arc here is greater than the area of this triangle, but it's less than the area of that triangle. So we could just write these out. So we know that the area of the arc is OAB. Now that there is equal to x upon 2. Now we know it's x upon 2 because the circumference is twice the area. Okay, so the area is the circumference upon 2. Okay, now that's one of them. Okay, now the second one we're going to look at, and down a bit, if we were to look at the area of the small triangle, well, this distance here is cos x, that's x there. This distance here is is sin x. Okay, so the area of that triangle is a half base times height, so I'll put in OCB, which is this triangle here, is equal to the half base, well, that half times the basis, cos x, and the height is that height there, which is sin x. And finally, the bigger triangle OAD, the area of that again is half base. Well, the base of this is just that length is just 1. Okay, it's just the circumference of that circle. Okay, which is 1. So it's going to be a half of 1. So it's a half times this height here. Well, this height here is just going to be our value tan x. Okay, so that's just equal to a half tan x. Now, again, we've said that x upon 2 is going to be greater than our half cos x sin x, and it's going to be less than our half tan x. Okay, so now we can get rid of the factors of 2, so we'll have cos x sin x, okay, and you'll have x, and you'll have tan x. So x is greater than cos x sin x, and it's less than tan x. Now we can divide throughout by sin x, so you have x upon sin x, okay, which equals, now we just cancel the sin x, so we end up with cos x, and you can x upon cos, divide throughout by sin x, so tan x upon sin x is, you'll just be left with 1 upon cos x. And then if we were to invert this, okay, so that would be, I'll write that again. Okay, so we invert that, so we'll have sin x upon x, okay, and we can say that's less than 1 upon cos x, and that's less than cos x. Okay, so we know that cos x, the limit is cos x tends to 0, right, the limit is x tends to 0 of cos x, well let's see, we know that equals 1, okay, cos x just looks like that, okay, and the same thing can be said about 1 upon cos x, the limit is x tends to 0 of 1 upon cos x also equal 1. Okay, so it means that as we have the limit as each of this tends to 0 equals 1, the limit as that tends to 0 equals 1. Now this sits here in between them. Okay, so by something actually called the squeeze theorem, but we don't need to get into that. Common sense can tell us that if this is less than that, and that tends to 1, and this is greater than that, and that also tends to 1, this must be squeezed in between them. Okay, so this must also tend to 1. Okay, so there you have our sin x upon x, and that's the limit as x tends to 0 as that is going to actually equal 1. Okay, so that's a little proof, and so thank you for listening, and goodbye.